Every number tells a story. Some count objects, some measure distance. They seem to appear almost randomly. Sometimes they are close together. Sometimes they are separated by surprisingly large gaps. But does the list ever end? Surprisingly, mathematics already knows the answer. So, let's assume there is a largest prime. Let's call it P. These are all the primes up to P. Now let's multiply them and add 1. This number is 1 more than a multiple of every prime. So, can any old prime divide in? Divide in by 2. Doesn't work. There is always a remainder of 1. So none of the old primes can divide n. So either n is prime, or n has a new prime factor. Either way, a new prime appears. There is always another prime. But how do we find them? But how exactly do we find primes? First, let's look at all the numbers from 2 to 50. Let's start with 2. 2 is prime. Now we can cross out all the multiples of 2 since they're all divisible by it. Therefore, they're not prime. All the untouched numbers are prime. Now, let's do 3. Five is still untouched. Next is 7. Now every untouched number is a prime. But why can we stop at 7? The square root of 50 is around 7.07, meaning every composite number below 50 has no factor above 7. This way to find primes is called the Sieve of Eratosthenes. And these are the primes below 50. We were right. But primes are more useful than just for finding them. Every number has a hidden structure. The hidden structure inside numbers. Let's take 84 and break it into smaller factors. We get 2 times 42, so 84 is divisible by 2. Let's break 42 into 2 times 21. And as we break further, every factor becomes prime. 2, 3, and 7 are all prime. This is called prime factorization. But we can write it more compactly. The exponent means that there's 2 factors of 2. And if we multiply the factors, we'll get back to 84. The key idea is that every whole number can be broken down into prime factors. And even more interesting is that every prime factorization is unique. No matter if we break 60 into 6 times 10 or 4 times 15, we'll get the same answer. Prime numbers are more than numbers that can't be divided evenly. They're the building blocks of arithmetic. But why are primes the building blocks? Let's take some primes and start multiplying them. Two primes combine to create a new number. Let's add another prime factor and another. Like this, we can build every composite number. Primes are the building blocks. If you change the blocks, you change the number. Every number has a foundation, prime numbers. This is the fundamental theorem of arithmetic. Prime factorization is essentially unique, and this is where primes become useful. But why are prime numbers so important? Imagine sending a secret message, but anyone could intercept and read it. So you encrypt it, meaning you turn that readable information into meaningless slop. What's interesting is the math behind encryption. Multiplying two large primes is easy. But recovering the factors from the product is very difficult. With small numbers, factoring is easy. But imagine numbers with hundreds or thousands of digits. So to encrypt, you just multiply. To decrypt, you divide by a key. This idea is used in RSA, a famous public key crypto system. So, where do primes matter? They're important in secure communication, digital signatures, and much more. A simple property of numbers can protect information. But primes can have even more surprises. Prime numbers are way stranger than they look. Let's take the primes between 0 and 50. At first, the primes seem to appear randomly everywhere. But look at the gaps. The distance between consecutive primes can grow with their size. And sometimes, it's very surprising how large these gaps can get. For example, between 1,327 and 1,361, there's a gap of 34. But sometimes, the opposite is the case. Sometimes, there are gaps of just 2. Primes that differ by exactly 2 are called twin primes. But do twin primes continue forever? We don't know. This is one of the most famous unsolved problems in number theory. And then, there's something even stranger. There is no simple pattern telling us where the next prime will appear. Yet mathematicians keep finding cues. We can prove many things about primes, but some of their deepest secrets remain unknown. And this is what makes primes so fascinating. So, what have we learned today? Primes are the building blocks of integers. They can be used to protect information, and they still hide unanswered questions. And the list keeps going. And then there are more. So where does the list end? It doesn't. There is always another prime. Euclid proved this more than 2,000 years ago. and the story never ends.